All right, so I hope your mastery tests from the other day went well. I know many of you still have upcoming portions of that. I wish you luck on those, but we're going to continue using our derivatives for things and talking about visualizing accumulation and rate of change from one another's graphical representations or table representations, but we'll focus on the graphs today. So I did want to address before we go on to anything else, this was what we talked about right at the end of class, the issue with the twos, like why the twos are in different places, because it's kind of weird, but there is a reason that they are in kind of non-symmetric locations here. It has to do with, so remember, if you have a function, let me call it, if I have a function y, I'm just calling it by its dependent variable name, and I want to take its derivative with respect to x, I can say I'm taking a derivative with respect to x of function y, which we then call dy over dx. So in a sense, these two, if it's not really what's going on, but just notation-wise, those last two expressions for the derivative here, if the function is just being called by y, it looks kind of like we're doing multiplication, like d over dx times y over 1 would look like that. It's not actually multiplication, but in the same sense, if I have dy over dx and I want to find the rate of change of that, or in other words, how the rate of change is changing, if I think about taking the rate of change of dy dx, or thinking about writing it on the top, dy dx, with respect to x is how we're finding these changes. You can see that either one of these, if you did the same sort of weird, pretend it's multiplication, it's not really multiplication, it's an operation. In the numerator, there's a d and a y, and in the denominator, there's dx and another dx. So notation-wise, it kind of looks like it's multiplication, but we're kind of missing the parentheses around the dx. That's not really what's going on, but just notation-wise, that's why the d's are kind of put in different positions there, just to indicate we're taking a rate of change of something that's already a rate of change with respect to still the original simple variable x, independent variable of the original function. So it's not, we're not treating the y's and the x's the same when we're looking at this second derivative. We're doing something slightly different because we're looking at how changing x changes dy dx, as opposed to looking at how x changes y again and then like doubling it or squaring it. So that's why the notation isn't like symmetric in terms of why the twos are in different spots. But in any case, regardless of why the notation is how it is, any of those notations with these little twos in there would indicate a derivative of a derivative or a second derivative. You can also do third derivatives, 17th derivatives, etc. Some of those don't have a lot of meaning, but theoretically you could continue taking derivatives of functions to see how the rate of change of the rate of change of the rate of change of the rate of change changes. I just don't know that that would actually help you solve a lot of problems. But second and third derivatives are actually used fairly frequently in applications. Just beyond that, maybe not so much. So in any case, getting back to this, I want to talk a little bit more about the patterns we were talking about last time between how positive and negative aspects of one function's values relate to increasing or decreasing in another. Specifically, if I have a function's output y, and I know that it's increasing, so I have an accumulation function, maybe think of this, and I say that it's increasing, what that indicates to me, the y values are getting larger and larger and larger, or that the rate of change, if the y values in a function are getting larger, the rate of change of that function would be something positive, right? So it doesn't actually matter whether I'm talking about an accumulation function or a rate of change function or a rate of change of a rate of change of a rate of change. If I know something about any sort of function, its dependent variable, whatever the meaning of that might be, is increasing, then that function's rate of change is something positive. That's what it means for something to be increasing. As the independent variable increases, the dependent variable increases, and that ratio, changes in the dependent to changes in the independent, that would be a ratio of two positive numbers. Therefore, we'd have something positive. So y increasing meaning that the final value is greater than the initial. If you're thinking like final minus initial to get change, so final be greater than the initial. Dx, we're assuming that x is getting larger. That's part of the, as we increase the independent variable. So since I have that change in y greater than 0 over a change in x that we presumed to be greater than 0 because that's how we were setting this up, then we have an m, this ratio dy to dx, that's positive. And again, it doesn't actually matter if y is an accumulation or a rate or whatever this dependent variable means. It doesn't change the outcome of this result. If I have a function whose dependent variables are increasing, dependent variable values rather, are increasing, that means that the rate of change of that dependent variable with respect to the independent, dy dx, is going to come out to be something positive. Similarly, if I have a function whose output or dependent variable values are decreasing as x increases, or as the independent variable, whatever it is increasing, then that would indicate, graphically speaking, going downhill. Or as x increases, y decreases, that means the rate, if I do the same sort of computations, the rate of change of y to x is going to be a ratio of a negative with a positive, coming out to a negative result. So whatever, you could pick some particular values to see this, but just if I have a function whose output is decreasing, then I know that a final and initial value of that dependent variable would be, well, the final one would be smaller than the initial one on that interval where I was talking about it decreasing. So if I do this subtraction to find dy, final minus initial, I'm going to get something negative. And then a negative divided by, as x increases, a positive value for dx would give me a negative value for m. And so this is stuff we've talked about since forever ago. But graphically speaking, if you have something left to right going uphill, we say that that dependent variable is increasing, or we could say that the rate is something positive, regardless of exactly how uphill it's going. Or if I have something that I've graphed, whatever the dependent variable's meaning might be, but something graphed where from left to right it's going downhill, on the interval where you see it going downhill, doesn't have to be a straight line, can wiggle around, but as long as it's becoming lower y values, we say that the rate of change during that is negative. It doesn't have to be one negative value rate of change. It can be a variety of negatives, but if it is going downhill or decreasing in general, then we say that the rate of change or rates of change are negative. So just keep in mind, be very careful when you're reading questions. You're going to have an assignment over this weekend where it keeps going back and forth between talking about positive, negative, increasing, decreasing. Make sure you're very careful which function we're talking about. So if I have a value of a function that's increasing, that means its rate of change or its derivative has a positive value in that same moment. Or if I had a value of a function that was decreasing, that means it has the derivative of that function has negative values in that same moment or in that interval that you're talking about. It doesn't have to be just small moments. You could talk about not having one particular value necessarily, but if over an interval my function is decreasing, then over that interval there are only negative rates of change or derivative values for whatever we started with. And so this applies if I'm talking about some function that I'm calling f, some accumulation function, and its first derivative, because I have a value of a function and value of its rate of change or its derivative with respect to independent variable, whatever it might be, typically x for generic purposes. But this is also true if the original function I was looking at was the derivative of something else. Whatever this function might be, if f prime, the derivative of f, is increasing, that means that f's second derivative, f double prime, f's second derivative would be positive. So if a rate of change is increasing, then we say that the rate of change of that rate of change is positive. A little bit more confusing to say that, but it doesn't matter what sort of function I'm talking about. Again, whether it's an accumulation or derivative or whatever, if I have some function that is increasing in its dependent variable values, that means its derivative has positive values. If I have some function that's decreasing during an interval, that means that its derivative is negative. So, bugs. one other thing to talk about, just in how an accumulation function, how you can see the second derivative just by looking at it. So you can see first derivatives in graphs just by thinking like slope, like going up, going down. So going up is positive, going down is negative, derivative of the thing you're looking at. If you want to see the second derivative of the thing you're looking at, we talked about that very briefly just with regard to one particular graph we're looking at on Wednesday. But if I have, like this first example that's here in green, if my original function is increasing and its derivative is positive, if my original function was accumulation, then this would mean going uphill. If this original function was a first derivative of something else, and I'm actually looking at a graph of the accumulation to see a rate of change of something increasing, a rate of change increasing could be a positive slope, a positive rate of change becoming more positive, or it could be like a negative rate of change becoming closer to zero, because that would be an increase, or something essentially zero rate of change turning positive for the first time. So any of those would be instances of a rate of change increasing, which would mean its derivative, the second derivative of the original, would be positive. So the graph of something like that doesn't have to be a full swoosh like that, but just thinking about the aspects of this. If I had a graph that was going downhill but curved upward, even if it's just a little portion of this, let me change to something other than black. I get it? Okay. So maybe at this point I have derivative values about -1. And then in a moment a little bit later I have a derivative value that's -0.2. That's an increase. If it continues increasing to, well, around this section, this looks like essentially straight across. So if this is a graph of f and it's going essentially straight across, that would mean that the derivative is essentially 0, or the rate of change is near 0. Maybe a little bit negative on the left and a little bit positive on the right, but in a small moment it gets closer and closer to just being 0 rate of change. And again, going from left to right, if I had a full graph that continued like that, that'd be fine, or even just any part of this. This curved up, kind of like it's part of a ledge that could potentially catch water if you poured it down from above. This curved up is how you can see, without having to think about the first derivative separately necessarily, you can see that a second derivative, or the rate of change of the rate of change, is something positive. Because we go from, if we're on a downward slope, from steeply downward to less steeply downward, or even to flat across, or on an upward slope, going from not very steep or even flat across to something where we do have slightly positive rates of change, or maybe even quickly to high positive rates of change. But at a spot like this, maybe f prime is 0.1. And out here, maybe f prime is 0.7. I'm just making up numbers. But from left to right along this, if I were just estimating somehow or another, maybe measuring some things, the values of that first derivative that I would compute would certainly increase all along from left to right. The first derivative was first negative, then 0, then positive, which is an increasing sequence of numbers, regardless of exactly what the sequence is. But just if I have that rate of change of the rate of change positive, that means that my first rate of change, my first derivative, is increasing. First derivative increasing in a graph, Cartesian graph, would look something like this. So similarly, if I have a function that's really a derivative that's decreasing, and I want to talk about its derivative being negative, then I can think about a second derivative negative as being, well, kind of the reverse of what we just talked about. A second derivative negative indicates that a first derivative is decreasing. And a first derivative, or rate of change decreasing, could mean it goes from a large positive number to a smaller positive number, or a small positive to 0, or 0 to negative, or it could be the whole sequence of events, something like this. But a shape of this sort, or any portion of it, if you see that in a Cartesian graph, you can think, oh, my second derivative, or the rate of change of the rate of change, is negative. The rate of change in this is decreasing throughout, meaning the second derivative, rate of change, is negative. So this is positive, lower, lower, near zero into negatives, more negative. That's a decreasing sequence of, possibly estimated slopes, if you wanted to, those rates of change in small moments around that curve. So in any case, just wanted to point out, curvature can tell you about the rate of change of a rate of change, or how the derivative is changing, what the pattern is. So if I'm talking about an accumulation function decreasing, say, oh, that means going downhill or negative derivative. If I'm talking about a rate of change decreasing, that means my rate of change, I don't know whether it was positive or negative, but my rate of change is going from positive numbers possibly down into negative numbers, or in any case, decreasing in value, which would somehow or another cause our graph to curve downward, like a water would roll off the top, not ever catch it sort of situation. So I remember when I learned this, like the up faces up, that's positive like a smile, and faces down, that's negative like a frown. So in any case, negative second derivatives are sad, positive second derivatives are happy. Just shape-wise, if you want to have a quick way to think through something without thinking about it, but I prefer if you know why they are the way they are, not just what things look like. So what I want to do is take a look at some graphs, and let me just scoot this down a little bit. There we go. So suppose that this is a graph of some mystery accumulation function f. So I've got three questions for you here, A, B, and C. Some of them have the same answers. It's up to you to figure out which. But I'm going to highlight what some of these numbers are, since it's kind of hard to see the axes. This is counting by ones is what this is on the axes. Or in other words, let's see, right. This is 1, 2, 3, 4, etc. 1, 2, 3, 4. You don't really need the y values when we're doing this, but just look at this graph. It's a weird combination of polynomials and something else, but whatever it might be. Take a look at this graph and see if you can estimate, maybe just use whole numbers, on what intervals this function f is increasing and decreasing. The second question is on what intervals f prime is positive versus negative, or has positive or negative values, and on what intervals is f prime increasing or decreasing. So two of those questions, A through C, are the same as one another. The third is different, so let you think about which is what. But take a couple minutes, think about what intervals we've got here. We're going to talk about the function that you see, the accumulation increasing or decreasing, its rate of change being positive or negative, and its rate of change increasing or decreasing. Just estimate. It's hard to see all these precisely. This slightly better notation. There we go. All right, so the first question, A, I hope that sounds like something that you've done since like algebra classes, maybe algebra 2, where you look at a graph and describe where the function values, the y values, are increasing versus where they're decreasing. So starting from the left and moving rightward, this just does continue going up, as does that. So negative infinity to infinity is just our whole domain. But when I start out at the left end of the graph screen or domain, what is this function f doing? Increasing or decreasing? As I begin at like negative infinity or negative 5 or wherever, the function is decreasing. And it decreases until approximately a little bit past negative 4. I'll just round it off to whole numbers. But it seems to be decreasing from negative infinity through negative 4. And then it starts increasing. I'll just use negative 4. Let's say about there. It does increase, not for very long though, just to about negative 3. And then it's decreasing again until downhill till we get to about here. So I'll just call that 1, just rounding off to whole numbers. So decreasing from negative 3 through 1. And again, this union symbol just means, and by the way, there's this whole other unconnected interval. So negative infinity through negative 4, along with also negative 3 through positive 1. And then there's a second interval of increase as well. Increases from there on out, from 1 through infinity. So that covers the whole domain. Decrease, increase for a little bit, decrease, increase. Down, up, down, up. All right, so those sections there, there's 3 blue dots on there. None of those 3 dots is actually included in the intervals I listed above. The numbers associated with those points are listed, but I have open intervals here. Right at, if this is actually the point where it stops going up and starts going down, or right in this moment, the graph turns around there from going up to going down, what would you say about the rate of change of function f at this point? Is the rate of change, let's see, positive, negative, increasing, decreasing, none of the above? Yeah, it's about 0, essentially 0 around this x equals negative 3. So I'll just say f prime of negative 3 is approximately 0 at that peak there. What about at the other 2 blue dots? Same thing, right? I mean, there's some opposite stuff going on, but the rate of change at around negative 4, I declared it negative 4 up here, around negative 4 here, the graph was decreasing and then increasing. The rate of change when we aren't decreasing and aren't increasing, it's kind of one or the other, or transitioning, it's also essentially 0. So I'm just using negative 4, doesn't look like it's exactly at negative 4. But f prime of negative 4 is essentially 0. And same thing here at what is declared to be x equals 1. In this moment here, wherever this is precisely, it looks like 1. But the rate of change at that lowest point there is essentially 0, meaning we don't have something that has a positive rate of change, nor is it negative. So which sections of the graph have a positive rate of change? Because that's what's asked next. On what intervals is f prime of x positive? First of all, how many intervals are there where it's positive? There's 2. Okay, and they correspond to 2 of the ones we just listed above. Positive rate of change is the same as increasing y values. So if f of x is increasing on these intervals, then f prime of x is positive on those exact same intervals, negative 4 through negative 3, and also this other section, 1 through infinity. So the negative goes with the decreasing in the same way, meaning this left section is decreasing, also has a negative f prime. Here's a second interval of negative f prime values. So between negative infinity and negative 4, or also in the interval negative 3 through 1, I would have negative derivative values of some sort. Near 0 if I'm near these dots here, and not too close to 0 if I'm in the middle. Or far out here, extremely negative. So what about this part C then? If I want to know on what intervals is f prime of x increasing, is that the same as f prime of x being positive? Well, in some places, both of those are true at the same time. It's possible to have the derivative have positive values and the derivative be increasing, but those aren't the same thing. Just like looking at this graph, it's not the same to answer when are the y values positive and when are the derivative values positive. Those are two different things being positive. So if I ask when is this derivative positive and when is the derivative increasing, those aren't talking about the same things. Derivative increasing would mean maybe I have a negative derivative that's becoming less negative, closer to 0, or a zero-ish derivative becoming positive, that would be increasing. Or again, this would be talking about anything of the variety shape-wise that's something curved upward. Whereas a decreasing first derivative would mean in my graph of f, the accumulation, that I've got a downward curve. So if this is function f here, and I'm talking about when is f prime increasing, f prime positive is graph going uphill. F prime increasing is graph curved a certain way, because I could have positive or negative derivatives, but they just have to be becoming larger, as in negatives change to zeros, change to positives, or any portion thereof. So it doesn't really have to do with those dots that I have there. If I'm looking at where is f prime increasing, I've got extremely negative values that are becoming slightly less negative and then turn to 0. So that's all places where f prime is increasing. But it actually continues increasing up till maybe about here. And this is kind of hard to tell. It's a really small one. But curvature-wise, I can see that it was becoming more steep going upward, but then it kind of capped off and went over the top of a hill. So my derivative values, or my rate of change values, were extremely negative, and then 0, and then a little bit positive, and then they went back to 0. So sometime between being 0 and 0 again, there's a highest positive value, kind of, I don't know, maybe kind of in the middle. Those are they're hard to pick out precisely, but I'd say that between negative infinity and I'm not going to use a whole number this time. I'll use negative 3.5. This is curved upward, meaning if I were to estimate rate values along here, I'd have a sequence of rate values that was becoming larger, from a low negative to a higher negative, as in closer to 0, all the way to 0 and into the positives, before that rate started decreasing back to 0 and into the negatives. So in terms of this shape, I don't want to trace the whole thing, that'll be messy, but this portion of this is curved upward. So I've got a positive second derivative or an increasing first derivative. But then after that, I've got this curvature downward. So you can see that there's this downward curvature next from negative 3.5 through, well, I don't know, but there's definitely a positive curvature here, meaning rate of change is increasing. This is rate of change decreasing. So somewhere in between these two parts that are easy to spot, this derivative becomes as negative as it's going to be, or becomes as low as it's going to be, and then starts approaching back to 0 again. So the rate of decrease is fastest somewhere in here. I'm just going to say it's about at negative 1. Again, those are kind of hard to pick out. But then at negative 1, this begins with this most steeply negative, lowest negative number, and then becomes larger until it's 0, and then into the positives, and then continues increasing So past this point, we have all positive curvature, if you want to think of it that way, or our first derivative is increasing throughout, or our second derivative is positive throughout this remaining section. So it's very hard to spot, unlike tops and bottoms of hills, where you can turn around from increasing to decreasing. It's very hard to spot just visually where these kind of curvature changes happen. The name of those curvature changes, those are called inflection points. You'll do some reading about that if you haven't already. These inflection points are where we have curvature changes, visually speaking. But they indicate points where my derivative converts over from increasing to decreasing, or from decreasing to increasing. This point here is changing from increasing to decreasing first derivative at this spot. And at this spot, the first derivative changes from decreasing to increasing. Again, not negative to positive derivative, but decreasing first derivative to increasing first derivative. My derivative was becoming more and more negative, and then it started going back towards zero again, and then continued on past zero into the positives. But in any case, these curvature changes signal places like this spot here. This is the flattest spot in the immediate area, meaning the derivative was, well, it's not flattest. I would say it's least negative. It was increasing until it stopped. The derivative was increasing until it stopped increasing. That was the steepest upward curve that we had, and this is the steepest downward portion of the curve that we had in the immediate vicinity. Now, there's other stuff going on out here, but we had a derivative whose value was becoming more and more positive throughout until it reached this point, and then it stopped, and it started becoming more and more negative until it reached here, and then it stopped. And then the derivative was becoming more and more positive. First, it had to pass through the rest of the small negatives, more and more positive as we go on. So in any case, this last section, through infinity, sorry. This last section here, part C of this, is asking something different from part A and B. A function being increasing or decreasing versus its derivative being positive or negative, those are asking the same thing in two different ways. But a function's derivative being increasing or decreasing is not asking the same question as either of those. So let's reuse this graph for something else. Suppose that this is a graph of a rate of change function. And its name is, I'm just going to scoot this a little bit, f prime. And I want to know on what, let's see, intervals is, I'm not going to change these. These I'm going to leave the same. On what intervals is f of x increasing or decreasing? But this is a graph of f prime now. So we're looking at something else. So these questions are going to have different meanings for us. If this is a graph of a rate function. So remember looking at rate functions. This is what we started with all before your test too. Look at this graph of a rate function. I can see I've got positive rates and then negative rates and then, well, kind of zero there. Negative rates, negative rates, negative rates, and then positive rates. So in terms of on what intervals is my rate positive or negative, this is a graph of my rate. So if this is a graph of rate and I want to know where it's positive or negative, well, the intercepts, the x-intercepts, are what divide those, right? That would be like in the previous question if I asked you where are the y values positive or negative. We didn't answer that question, but so this is asking a different set of things just by changing what this is a graph of. So if this is a graph of f prime, I can ask you about f or f prime, and you should be able to answer questions about that. But on what intervals is f prime positive? Well, looks like negative infinity through that x-intercept. Let me call it negative 4.2, just so it's something to the left and it doesn't get confused with the last rounding that I did. And then, let's see, it's negative f prime, since this is a graph of f prime, is negative, has negative dependent variable values between negative 4.2 and negative 3. And then it's negative, 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 negative until we get to x equals 2. So notice this is 2 negative intervals in a row. At x equals negative 3, saying that the rate isn't negative, it's essentially 0. So this is f prime of negative 3 is approximately 0 just by inspection. And same at these other y-intercepts. Since this is a graph of rate, since this is a graph of f prime's about 0 when it's on the x-axis, when the dependent variable value is 0. All right, so let's see. Past 2, f prime, the rate, has all positive dependent values. So from 2 onward, we've got positive rate values. So I didn't change the questions. If you remember last time, question A and question B were asking the exact same thing. That is still true. Question A and question B are still asking the exact same thing. It's just we had to interpret the graph differently. Last time we were looking at an accumulation function, so we looked for when is it going uphill or downhill to talk about increasing or decreasing and to determine when the rate was positive or negative. Now we have a graph of a rate function. So if I'm looking at a graph of a rate function, I can see easily that the rate function is positive or negative by its dependent variable values, the y values in the graph. Which that means that if I were to sketch the original function f, it would have to be increasing this whole section to the left of negative 4. So my rate is going from a large positive number to a smaller positive number to 0. But that means that if I have rates that are large positives and then small positives and 0, I can maybe imagine my original function would be really steep and then less steep and then kind of top out right around x equals 4, negative 4. Negative 4.2 is the number I used here. But positive rate values correspond to increasing original function values. So whatever this was the rate of. Get this out of the way. So meaning the original function must be increasing them between negative infinity and negative 4.2, and then again from 2 through infinity. And we could try to sketch what that f might look like, but we don't really have any sense of how large or small its y values are. You can make up anything you want. All we have if this is a rate is it increasing or decreasing and how quickly? We don't know what its y values are unless I tell you something like that. But again, the other aspect to this, negative rate values correspond to decreasing function values, whatever function this is the rate of change for. So again, these A and B are the same question, just this time it was maybe easier to think about part B directly. Decreasing, negative 4.2 through negative 3, and then again from negative 3 through 2. So if I were thinking about what would the original function f look like, I probably don't want to graph it on the same axes, because in terms of if you had any context for this, the dependent variable values would have completely different units for an original accumulation function and its rate of change. So I wouldn't want the vertical axis to represent both like meters and meters per second. That doesn't really make any sense. So we wouldn't typically graph these on the same set of axes together. But if I were trying to imagine, I'm just going to use this space for a second, what the original function f would look like, I'm just going to center it around the axes kind of nicely. Well, f of x is increasing, and then decreasing, and then decreasing again after taking a brief pause, and then increasing. So uphill, downhill, downhill, uphill. So my key points are this negative 4.2, negative 3, and 2. And if I was trying to put together what's going on and fit it somehow in this window, I don't really know any y values, so I don't know how high or low this actually is relative to the x-axis. But I know that from the left end of the domain all the way to negative 4.2, function f is increasing somehow or another. And then after that it decreases pauses for a moment, and then decreases again. So maybe I'm going to have this, let's see, wherever this function f is, it's going to increase until I get to this negative 4.2, and then decrease until we get to 3, pause for a little bit, and then decrease again, only increasing again once we pass this x equals 2. Now, I just drew straight lines, more or less, meaning that would indicate one constant positive rate and then a negative, 0, negative, and then one positive rate again. But this isn't one positive rate. This is an extremely high positive rate becoming closer and closer to 0. So it's not actually like this. I'd like to know the curvature by thinking about what's going on here. Now, answering question C is something that we did in the last graph. Like, okay, I have a graph of f prime. Where's f prime increasing? That would be looking at the graph. Where is this graph going uphill? This is a graph of f prime. If I want to say where's f prime increasing, I want to know where's f prime going uphill. Well, let me pick a different color here. F prime's going uphill briefly from this spot here to that one. And that's about, let's see, until we get to here, onward. Those two intervals is where f prime is increasing or going uphill. So we went from very slightly negative back to 0, and then from negative 3-ish up to, well, extremely positive values. But f prime is increasing from about negative 4 through negative 3, and then from positive 1 onward, whereas it's decreasing the rest of the time, meaning negative infinity to negative 4 and negative 3 to 1. But f prime increasing still means concave up. F prime decreasing still means concave down in terms of if I were trying to sketch a graph of f, the thing whose rate this is. So if this is supposed to be a graph of f we're putting together here, this was negative 4.2, negative 3, and positive 2, the values that were key in putting together its increase-decrease portions. If I want to talk about how it's curved, some of it's kind of the same, but this portion between negative 4 and negative 3 should be curved upward, although decreasing most of the way at least. And then from 1 to infinity, it's curved upward again. So maybe from about here, I'm going to make this curve upward. So just kind of going with the same patterns of up versus down, but making it curve a certain direction. And then in between, I've got to have this curve downward here. And it does have to connect, but I'm not very good at making my pen go where I want it to. And then before negative 4, I was curved downward, and also this is where the function was increasing. So before negative 4 it was, so there's this kind of turnover where it changes curvature and then it hits this top part. This is not an easy function to recreate, but you can put together some pieces and facts based on where the rate f given is positive and negative, where the rate is increasing, decreasing, because, well, we have how those are related to one another. So with looking at a graph of an accumulation function, it's usually easiest to see where's that graph, or we've done it a lot, increasing or decreasing. So just keep in mind that where an accumulation function is increasing or decreasing corresponds to its derivative being positive or negative. But also adding in the curvature part, if you see an accumulation function that's curved upward or curved downward, that's the rate of change being positive for upward or negative for downward. So, rate of change increasing for, sorry, talking about two different things in my mouth at the same time. So if you see an accumulation function that's curved upward, its derivative is increasing, meaning the second derivative is positive. Or if you see an accumulation function curved downward, that means that its rate of change is decreasing, or its second derivative of accumulation, is negative. So, in any case, what you're going to have over the weekend for some things to do, there is an iMath AS assignment where you're doing things similar to this. You're given a graph and you're told whether to consider it to be F or F prime, something like that. Ask some question about increasing, decreasing, essentially zero, positive, negative, those sorts of things. I also have for you a take-home quiz, which is on some of those same things, lower difficulty level, just a couple of extended problems on that, and giving you a chance to explain what your thought process is. And there's going to be some reading. So that's about it, but don't go before you get one of these. I will post this also in case you lose it. Or want a new copy of it. Or just have to print out math papers.